All right, stack canaries. One of the earliest defenses that was proposed. The idea is these smashing the stack attacks that work by overwriting past the end of a buffer, overwriting return address, and redirecting control of execution of the program. You say, well, that's really bad. Let's try to find a way to detect if that's happened before the malicious code starts executing. So the idea of the stack canary is that we're going to modify the stack layout. We're going to insert an extra 4 bytes, say, an extra word, just before the saved return address on the stack. So that's where the pictures of that cute little peep is. That's the stack canary. And a stack canary is a random value that's chosen randomly when the program starts up. So imagine the program randomly chooses a 32-bit value. Every time you do a function call, after you save the return address, the first thing that function is going to do is it's going to go look at the stored stack canary and save it in the stack. It's going to write that value, secret value, in the stack. So this is randomly chosen. It's not disclosed, so it's secret, so hopefully the attacker won't know it. The function is going to store that in there at the start of the function. And at the very end, just before returning, the function checks to make sure that the value that's in there matches the stored value, what it wrote initially, to make sure that it hasn't changed. If it's changed, oh my gosh, it should never change. Because the only code that ever touches this is going to be the stuff we wrote at the beginning and end of every function. If it changes, like, holy cow, someone's trying to exploit us. So, like, shut down the program. We're under attack. But if it hasn't changed, then the idea is then we go ahead and return. We go ahead and use that return address. Okay? So the hope is if there's a buffer in here somewhere that's stack allocated and is overflowable, when the attacker tries to exploit the buffer overrun vulnerability, they'll start writing past the end of that buffer. Some of the code inside our function will start writing past the end of that buffer, and it'll keep writing, and it'll eventually overwrite the return address. But before it can overwrite the return address, it has to overwrite the canary. So the canary is going to get trashed. So that should be detectable because the canary should change. Okay, so that's the idea of the stack canary defense. Okay, great. So you're already starting to think, how could an attacker try to bypass this? So you're thinking, if the attacker could read the canary, then they're in like Flynn, right? Then they're golden. Then they know the value. They can make sure when they overwrite it that they overwrite it with the correct value. So we're going to have to ask ourselves, is there a way that the attacker could learn that value? Huh? Yep. That's true. If I check, when I check the canary value, if I notice it's changed, like, oh my gosh, I don't know how much of memory might have been changed. It might be stuff that's trashed all over the place. So there's no way to like keep going. There's no way to patch things up, and because it's arbitrarily bad at this point. So really, all you can do is crash the program immediately. Recovery might be hard. Yeah, I don't know how to do recovery. So in practice, the way people implement this is they just cause the program to terminate if that happens. They don't try to recover. Yeah. Why are they called canaries? It's like the canary in the coal mine. It's the birds are very sensitive to toxic fumes, and so you take the canary down into you with a coal mine, and if the air starts getting bad, I mean, it's kind of grim, but the canary keels over, right? And that's the indicator that, whoa, look out, there's badness happening. Same thing here. If that canary keels over, if it gets overwritten, that's the indicator that something bad is going on. The very back, yeah. Same canary for every function. Yep. Typically, we do the same canary for every function to avoid having to generate a lot of random numbers. Yep. Yeah, it might be stored somewhere in memory in some global variable. Can you mess with it? Yeah, that'd be another kind of attack to imagine figuring out how to mess with it, like overwrite the canary and overwrite the stored value as well. Yep. Yeah. Why does the attacker need to write over the canary? Well, there's an assumption this defense is making. The assumption is that there's a buffer overrun in a buffer here, and that overrunning the buffer will cause it to consecutively write bytes into the buffer and beyond, and will just keep writing things with no gaps. So if that's true, then then you can see that before the return address gets overwritten, then the canary also has to be overwritten. If there was a way to write with gaps, then the canary might be useless. Yeah? I don't know whether I'd call it violating security through obscurity exactly, because using stack canary, you can tell everyone I'm using this. You can give them all the code. Like compilers implement this now, so they'll automatically insert this at the beginning and end of every function call. So there's nothing secret about the design. It's true that canary is secret, but that's chosen separately for each time you run the program. So that's kind of like a password. So that's okay. So I think it's not a problem of security through obscurity. The problem is just this defense is just darn weak. And you just talk through a whole bunch of ways that you might be able to bypass this defense. And it depends on the nature of the bug in your code. It depends on exactly what kind of vulnerability there is. Is that a stir copy that writes consecutively, or is it something else that writes with gaps? If it's a format string vulnerabilities allow the attacker to write anywhere. Can the attacker read stuff in memory? If there's two vulnerabilities in your program, one that allows the attacker to read stuff in memory, and then the another one allows to do an overwrite, you can use the first one to learn the canary value and then overwrite it. You can overwrite stuff in the heap instead of stack allocated stuff. This doesn't protect against that. You could overwrite stuff other than the return address if there's a function pointer or a C++ object on the stack. There's any number of cases where it might be possible to bypass this. Okay, so this is a pretty weak defense. Maybe what you could say is it raises the bar for attackers, that they have to find one of these extra vulnerabilities or hope to land in one of these situations, but it's still pretty weak. And basically the only reason we use it is because it has basically no performance impact. So I wanted to start here to give you an idea of the style of hardening defense and also the flavor that these are not guaranteed. And then on Monday, I'll show you some better hardening defenses. Have a good weekend. Don't forget to turn in homework 0.